Okay, so this week we're going to start talking about functions. So let's get a few definitions and then we'll see some examples. A relation is any rule that associates any x value with any y value. You can think of a relation as any set of points. So here's an example. 0, 1, 0, 3, 2, 3, 4, 7. It's just a collection of points. And notice our points don't have to be in numbers. So we can associate Rob with green, Diego with blue, Tamara with red, Sal with black, Tiana with yellow, and that's still a relationship. So, or relation rather. It's any kind of relationship between two things that are expressed as an ordered pair. Okay? Now, a function is a very special kind of relation. A function is a rule which associates exactly one y value to every x value. Or if you want to think of it this way, a function can't have repeating x values. So with that in mind, we cannot have repeating x values in a function. Let's take a look at these two examples and decide if they're functions. Let's just look at the x values. So notice 2, 1, -3, 4, 9. Those are all different numbers. So this one is a function. On the other hand, let's look at B. 8, 7, -2, 8. We can't have repeating x values. So we have two x values that are the same. This is not a function because it's got those two 8s. Okay? All right, so let's get a few more definitions. The domain are the x values of any relation, and the range are the y values of any relation. So let's find the domain and range of these two relations that we had up here in A and B. So I labeled them A and B just so it would be easier for us to write them down here. So let's get A's domain. A's domain is all of its x values. So 2, 1, -3, 4, 9. And this notation I'm using with the set brackets is what we use when we're just making a list. Notice that when we're making a list, order doesn't matter. I can put them in any order I want. All right, and then let's get the range for letter A, and I probably ought to just kind of put a colon here to say this is all for letter A. All right, so A's range is its y values. So 3, 5, 5, 2, 3. Now, I really don't want to list the same things twice. So 3 occurred twice and 5 occurred twice. So we'll just list 3, 5, and 2. And again, order doesn't matter. We're making a list. Now, later on, we'll see that order does matter when it's not a list. All right, and then B, let's get its domain. And it doesn't matter that B wasn't a function. We're just getting the domain, and all relations have domain and range. So let's list the domain for B. 8, 7, -2. Again, let's not list the same thing twice. So we don't want to list 8 twice. So 8, 7, -2, and 9. And then finally, let's list its range. And that is going to be 9, 2, -9, 4, and 1. Okay, so it gets a little more complicated when we're trying to list the domain and range for algebraic functions. And for the most part in this class, we'll concentrate on the domain when we're dealing with an algebraic function. And later on, we're going to learn how to graph it. And then we'll be able to pluck off the range from the graph because it's far easier to tell range from a graph. But let's look at we're going to look at 3 specific types of functions and find their domain right now. Later on, we'll add more to what we find the domain of, but polynomials, the domain of a polynomial is going to be everything, all real numbers. There won't be anything we can't plug into a polynomial. Now recall, a polynomial, take that off to the side. Recall that a polynomial has x's with integer, or I'll say counting number exponents. So 1, 2, 3, 4, 5, etc. Okay, so counting numbers for their exponents. So we'll see an example of a polynomial here in a minute. We're going to look at rational functions. That's anything that's in fraction form. So we'll determine where the denominator is 0 for those, and we have to exclude anything that makes our denominator 0. So we'll see an example here in a second. And then radicals. Of course, we solved a couple of weeks ago, we solved radicals, radical equations. Now we're looking at radical functions. If we have an even root, we're going to determine where the stuff inside of our root is greater than or equal to 0, because we can only have positive numbers or 0 underneath a radical, an even radical. An odd root, the domain is all real numbers. Okay, so let's look at examples of all of these. We're going to first find the domain of A. We have this function, and notice that with this function right here, all of our x's have counting numbers for their exponents. Even this x right here, it's really to the first power. We just never write to the first power. Remember, if a power isn't written, we assume it's 1. So this has all counting number exponents. It's a polynomial. Its domain is all real numbers. Now, there's two ways to write this. All real numbers, but probably in my open math, you're going to have to write the infinity symbols. So we're going to have negative infinity to positive infinity. And let's see, there it is. Negative infinity, which looks kind of like a sideways 8 to positive infinity. That's our domain. So either one of these will suffice on a test for you to say all real numbers or negative infinity to positive infinity, but probably in my open math you're going to need to put negative infinity to positive infinity. All right, now B, let's notice, is a fraction. All right, so according to the rules that I wrote up above, we need to determine where the denominator is 0, and we're going to exclude those values from our domain. So I'm going to take my denominator, which is x squared minus 2x, whoops, darn it, minus 2x minus 8, and I'm going to set that thing to 0, and I'm going to solve that equation so I can determine what things cause this denominator to be 0. All right, so we can factor that thing. It factors as x minus 4, x plus 2. Remember, factors of negative 8 that add to minus 2. Set both of those to 0. And when we take our 4 over, it will become a positive 4. And when we take our 2 over, it will become a negative 2. These are the two places that cause this denominator to be 0. So I have to exclude them from my domain. Now, on a test, you can write all real numbers except x equals 4 and x equals negative 2. However, in my open math, they're probably going to want interval notation from you. So if we write this in interval notation, we're going to go from negative infinity, and actually I need to put a negative in front of my infinity symbol, up to the first value. Now on the number line, if we're thinking left to right, or going from left to right, negative 2 will be the first one we come across when going from negative infinity. And then the union just means also. We're going to go from negative 2 to 4, and then we're going to go from 4 to positive infinity. Okay, so left to right. Notice that I'm using the open brackets, meaning negative 2 is not included in our domain, and right here, 4 is not included in our domain. Now, another way that you might also see this written is you might see x not equal to 4 x not equal to negative 2. Oops. X not equal to negative 2. So there's really 3 different ways we can write that domain. All real numbers except 4 and negative 2. We can write the interval notation with the open brackets, which leave out the 2 things that we're supposed to exclude. And we can also write x naught 4 and x naught negative 2. And it could be that my open math asks you for this. So just watch what it's asking for there in the answers. All right, now let's go to C. Let's notice that we have a radical. We have a square root. A square is a 2 for the root, so that's even. Even roots, notice what it says, determine where the radicand inside of the root is greater than or equal to 0. So this is actually not too bad. All we're going to do is take what's underneath the square root, and we're going to set that greater than or equal to 0, and we're going to solve it. All right, so let's add 9 on both sides, of course. That's going to give us 3x is greater than or equal to 9. And then let's divide out our 3. And when we divide out our 3, we end up getting x is greater than or equal to 3. Get my greater than or equal to symbol again. Now, remember when we were talking about interval notation and inequalities, this would be equivalent to 3 to infinity in interval notation. All right, so there's our domain. All right, now D is actually an easy one, and this is very small, kind of hard to see, but that is a cube root or a third root, a 3 there for our root. And notice odd roots, our domain is all real numbers. So this one's easy. It's all real numbers. Or, as we did with the polynomial, we might need to put negative infinity to positive infinity instead of all real numbers. There is also a symbol for all real numbers. I don't think I can get it under the symbols here, but it looks like an R where somebody's put 2 slash marks on the stem of the R. So you might see that to denote all real numbers in my open math. Just kind of a funky looking R, capital R.